Astronomers have detected the first gamma-ray eclipses from a spider star system in which a superdense, rapidly rotating neutron star called a pulsar is feeding on a stellar companion. These never-seen-before gamma-ray eclipses are caused by the low-mass companion star of the pulsar moving in front of it and very briefly blocking high-energy photons. Hello and welcome to KYC News. Please don't forget to subscribe and hit the bell icon. An international team of scientists has found 7 spider systems undergoing such gamma-ray eclipses while scouring more than 10 years of data from NASA's Fermi Gamma-Ray Space Telescope. In one case, the finds helped the scientists to discover how a spider system is tilted in relation to Earth and to determine the mass of the pulsars in such systems. In the future, the research could help scientists define what mass marks the dividing line between neutron stars and black holes. One of the most important goals for studying spiders is to try to measure the masses of the pulsars. Colin Clark, an astrophysicist at the Max Planck Institute for Gravitational Physics in Germany and lead of the research team, said in a statement, "How spider systems are born. Like all neutron stars and black holes, pulsars form when massive stars run out of fuel for nuclear fusion and the outward energy that supports them against gravitational collapse ceases. As the core of such a star collapses and outer material is blown away in a supernova, the core's rotation increases massively, just like an ice skater drawing in their arms to speed up their rotation. The core collapse results in a neutron star, a body with the mass of the Sun or more crammed down into a diameter of around 12 miles, 17 kilometers, about the width of a city here on Earth, so dense that a mere teaspoon of it would weigh 4 billion tons, the equivalent of 600 Great Pyramids of Giza stacked on a spoon. If the star is massive enough, the inward force of gravity overwhelms this material, which is 95% neutrons, and forces a complete collapse that triggers the birth of a black hole. Quite where the dividing line isn't clear, however. Pulsars are basically balls of the densest matter we can measure, Clark said. The maximum mass they can reach constrains the physics within these extreme environments, which can't be replicated on Earth. Pulsars are also considered extreme stellar remnants because they blast out intense radiation. Because these beams aren't aligned with their axis of rotation, they sweep across space, with their emissions appearing as pulses in regular intervals as they turn to face Earth, almost like a cosmic lighthouse. Scientists believe that spider systems form when one star in a binary system evolves faster than its partner, forming a pulsar with beams of light, including gamma rays, sweeping in and out of our view on Earth. Early in the pulsar's existence, it feeds on material from its binary companion, dragging this material away in a stream of gas that carries angular momentum. The accretion of this gas onto the pulsar adds angular momentum to the stellar remnant and speeds up its rotation, or causes it to spin up. As the pulsar spins more rapidly, it stops feeding and begins blasting high-energy particles and radiation at its stellar companion, superheating and eroding the side of the star facing the pulsar. These spider systems are divided into 2 categories with suitably arachnid-inspired monikers. A black widow system contains a pulsar and a stellar companion with less than 5% of the Sun's mass, while a redback system partners a pulsar with a larger stellar companion that has between 10% and 50% the mass of the Sun. In both species, female spiders sometimes eat their mates. Gamma rays put a tilt on spider system observations. Astronomers have been able to gather a wealth of information about spider systems from the light they emit. For example, visible light can reveal how quickly the companion is traveling, and radio wave measurements can reveal the pulsar's rotational speed. But these observations are based on motions toward and away from Earth and are therefore influenced by the angle at which these systems are orientated with regard to Earth. For systems we see face-on, changes in this motion are slight and can produce signals that look confusingly like those from a smaller, slower orbiting system seen side-on. That difficulty means knowing the system's tilt is vital for understanding that system and its mass. Astronomers can use visible light observations to assess the system's tilt, but these measurements can be complicated. For instance, if the companion star's superheated side moves in and out of view, it can create fluctuations in the system's visible light signature. Also, astronomers are only just beginning to understand the superheating of stars, so models built around different heating patterns can give different results. In a spider system, gamma rays are only generated by the pulsar, not the companion star, and are so energetic that they are unaffected by dust and debris in the system and can only be blocked by the companion star. So if the gamma ray signal disappears, astronomers can be sure that the pulsar was eclipsed by the companion star. It's an unambiguous sign that astronomers are seeing the system side on, letting scientists confirm the companion star's velocity and the pulsar's mass. But these gamma-ray eclipses had eluded astronomers, hence the new research. Spotlight on a spider. One of the spiders the team studied was particularly fruitful. PSRB 1957+20 was the first black widow ever discovered, identified in 1998. But in more than a decade of Fermi data, Clark and his team found 15 missing gamma-ray photons, the constituent particles of light. 15 photons may not sound like a lot, but it's a significant find because of how precise the timing of pulsars is. Originally, scientists calculated the tilt of PSRB 1957+20 at 65 degrees compared to our line of sight. This measurement, made using visible light, had resulted in the pulsar's mass being estimated at 2.4 times that of the Sun. The calculation made PSRB 1957+20 the heaviest known pulsar and sat right at the theoretical mass limit that divides a neutron star and a black hole. With the new data, Clark and the team calculated that PSRB 1957+20 is actually tilted at 84 degrees, reducing the pulsar's mass to 1.8 times that of the Sun, a measurement much more in line with neutron star formation theories. There's a quest to find massive pulsars, and these spider systems are thought to be one of the best ways to find them, Matthew Kerr, a co-author on the project and a research physicist at the U.S. Naval Research Laboratory in Washington, D.C., said in the same statement. They've undergone a very extreme process of mass transfer from the companion star to the pulsar. Once we really get these models fine-tuned, we'll know for sure whether these spider systems are more massive than the rest of the pulsar population. Not only does the new work mark a step forward in our understanding of spider systems and pulsars in general, but it exemplifies the impact of the Fermi Gamma Ray Space Telescope on high-energy astronomy. Before Fermi, we only knew of a handful of pulsars that emitted gamma rays. Elizabeth Hayes, Fermi project scientist at NASA's Goddard Space Flight Center in Maryland, said in the statement. After over a decade of observations, the mission has identified over 300 and collected a long, nearly uninterrupted dataset that allows the community to do trailblazing science. Scientists have discovered the first gamma-ray eclipses from a special type of binary star system using data from NASA's Fermi Gamma Ray Space Telescope. Scientists have discovered the first gamma-ray eclipses from a special type of binary star system using data from NASA's Fermi Gamma Ray Space Telescope. These so-called spider systems each contain a pulsar, the superdense, rapidly rotating remains of a star that exploded in a supernova that slowly erodes its companion. An international team of scientists scoured over a decade of Fermi observations to find 7 spiders that undergo these eclipses, which occur when the low-mass companion star passes in front of the pulsar from our point of view. The data allowed them to calculate how the systems tilt relative to our line of sight and other information.